Well, good morning, good afternoon, or good evening, depending on your time zone. Welcome to this HAProxy 2.7 feature run-up. Today we are going to go through the new feature of HAProxy 2.7. My name is Sébastien and I work at HAProxy Technologies as a system network and support engineer. Please feel free to ask all your questions in the appropriate panel at any time, and I will answer them at the end of this session. As usual, this webinar is recorded and it will be sent to you within a few days. Today, we are going to cover several topics. First, a quick introduction to HAProxy 2.7. Then we're going to see the most important changes, thread group and bandwidth limitation. And we will see some other changes. And I would be pleased to answer any question at the end of this webinar. So let's start with the HAProxy philosophy. Simplicity is a key concept, and anyone will be able to read and almost understand a configuration. However, we recommend that each configuration should be documented to help the future and someone else to understand its logic. High performance is our #1 priority by the use of event-driven model and lock-free multi-threading. For reliability, 2 releases are made per year. Even release numbers such as 2.6 are long-time support or LTS. 2.6 is supported until 2027, and all release numbers such as 2.7, this one, is supported about 1 year. Backward compatibility is important. Most of pre-2.0 configuration are still valid in 2.7. Deprecation warning are shown a long time in advance. Since a proxy is the main entry point of your platform, it's important to have a global overview. Many metrics can be collected using StatStocket, the log and Prometheus exporters. The default log format provides most information to diagnose an issue for each request. Please consult the documentation to understand all the fields. HAProxy is also expandable. You can write your own Lua script and agent stream offload processing engine. Again, check our website for more information about those features. The HAProxy ecosystem consists of several components. First, we have the load balancer itself. Today, we will talk about some new feature about the 2.7 release. The HAProxy data plane API, which is able to configure the HAProxy load balancer via an API-oriented interface. We also have a Kubernetes ingress controller, which gives you a way to route traffic into your Kubernetes cluster. HAProxy uses an event-driven model, which is incompatible with blocking processing. That's why you can use a SPO agent to process very time-consuming tasks. And the Lua scripting language is embedded into HAProxy and can help to achieve some complex tasks. You can see some of them using Google. At HAProxy Technology, we love open source and we encourage contribution from everybody. If you have developed a new killer feature, we'll be glad to merge them into the mainline. If you are not a developer, you can still contribute in many ways. Even if our documentation tends to be as exhaustive as possible, it still needs improvement and clarification. And if you are an experienced user, you can still share your knowledge with others on our community media, such as Discord, Slack, Reddit, Stack Overflow, etc. And don't be shy. We are glad to share blog posts, tweets, talks, and other kind of documentation that you may have. So let's start with thread groups and see if you need them and how you should use them. So before we talk about thread group, we should have a look at some numbers for the traditional threading models. Those numbers are like other ones in the presentation, just order of magnitude. You should not take them as it. On a single core CPU, such as this one at 3.70 gigahertz, HAProxy can forward about 80,000 requests per second in proxy mode, process up to 160 requests per second, 1,000 requests per second in local or cache mode, generate 255 RSA keys. This is for 4K RSA keys, or generate 2.5 ECDSA keys per second. Last year, we probably achieved 2 million requests per second on a 64-core Graviton instance on AWS. Please check our blog post about this story. In HAProxy, threads are configured within the global section. Most of you should know that. There is an internal limit of 64 threads for each proxy instance. The NB thread directive defines how many threads should be created. This value is bound to the number of available CPU. Note that if this directive is not explicitly set, one thread per core are created. The CPU map directive is used to map thread to CPU cores. Thread IDs start from 1 and CPU IDs from 0. You can also use the all keyword to select all the thread and all the CPU cores. When the threads are bound to a CPU, each proxy can be limited to specific thread using a deprecated keyword, which is process. And we will see more about that later. In this example, the thread 1 to 4 are bound to the first proxy, and thread 5 to 8 are bound to the second proxy. There is one important rule. You should only bind one thread per core, otherwise they can conflict each other. So before going deeper, we should need to understand how CPU are architectured. Intel is one of the most famous CPU manufacturers. Here you can see a simplified version of an Intel CPU. Again, this is not a real one. This is just an example. You can see some core IDs here from 0 to 7. The core ID attribution may vary on different factors, but this representation is the most usual that you can find on most systems. This CPU has 8 cores from 0 to 7, 4 real ones here, and 4 logical ones or virtual ones. This is called hyperthreading. All cores are connected to a single L3 cache. In other words, all cores share the same cache. You can see or check the CPU topology of your computer or server using the lscpu-e command. There are various other commands that can provide the same information, such as lstopo. You can check your distro for that, but lscpu is the most commonly used. The physical and logical core share the same L3 cache. So you can see that core 0 and core 24 are sharing the same L1 and L2 cache. So they are bound together. And same goes for the CPU 1 and the CPU 25, and so on for each of them. The L3 cache is shared among all the cores. You can see here the L3 cache is set to 0, meaning that we have only one L3 cache. Okay. There is a nice tool which is called C2C LAT, which can be used to measure the core-to-core latency. It shows the access time from one core to another. And we can have some order of magnitude here. This black diagonal here is set to 0 because it costs nothing to communicate from one core to itself. The purple lines here are from the virtual, the physical core and its logical one. We can see that it takes roughly 20 nanoseconds to communicate from one physical core to one virtual or logical one. And for all other core communication, it takes about 1000 nanoseconds from a random core to another random core. This means that if two threads need to work together, it's better to bound them to a physical core and the other one to its logical core partner. If the threads are randomly spread across the CPU, you can expect an overhead about 80 nanoseconds. If you're using more than two threads dedicated to the same task, there are chances that they cannot fit into a single physical logical pair, and then you will have some overhead when they are communicating the one to the other. AMD is also another CPU manufacturer. You can see here a simplified version of their new generation architecture, which is called Core Complex or CCX. The first big difference that you will notice is with the Intel CPU is that this one has multiple L3 cache from 0 to 3 here. Again, this is an example. This is not a real CPU architecture. This one has 17 core from C0 to C15. 8 of them are physical one here. And there are also some logical one, the other ones, the light ones. Each L3 cache on its core, like that, L3 cache and its core is called Core Complex or CCX. If I remember correctly, this feature has been introduced by the Xeon CPU in 2017, if I remember correctly. You can also use the lscpu -e command to see the CPU topology. Here you can see the main difference with the Intel one is that this output shows several different L3 cache. We have here up to 8 L3 caches. They are numbered from 0 to 7, and each of them have 3 physical cores and 3 logical ones. For example, the first CCX is from core 0, 1, 2, and 24, 25, and 26. All of them are working together. Same goes for the other ones. Again, we can also run a C2C LAT on this CPU, and we see a very big difference from the between the AMD and the Intel. We can see that the physical to the logical latency is about 20 nanoseconds. It's almost the same as we have on Intel CPUs. But we can see a random access from one CCX to another to another core inside the same CCX is about 50 nanoseconds. It's way faster than from Intel, but when one core is trying to reach another one, the latency grows up to 280 nanoseconds. As a comparison, the latency to access the memory is about 100 nanoseconds. So in other words, it's cheaper to fetch data from the memory than from the random core on the single CPU. Now you can start to understand and to see what a thread group can be useful for. We should group thread per core complex to get the best performances. So for the new thread group setup, you have several directives. You have the old ones, the current one, which is end the thread, which defines how many threads you want to create. And CPU map is how you want to map thread per second on a CPU cores. Now you can also benefit from new directives such as thread groups with an S. It shows how many thread groups you want to create, and the thread group is how you want to map the thread within groups you defined before. It's important to understand that only thread within the same group can work together. In other words, thread from group 1 cannot communicate with the one in group 2. The goal of this new directive is to group a thread by L3 caches or core complexes on AMD hosts, and we can also use it to go beyond the 64 thread limits. For optimal performance, it's important that thread group is a divisor of ND thread. You see, otherwise you will end up with an unevenly distributed thread. If you do not specify the thread group directive, HAProxy will compute how many threads will go into a group and will start filling up the first thread group, then the second one, then the third one, and so on. Well, this is an example how to configure a thread group and how to associate a thread to CPU core. You can notice a few things. Group numbers start from 1 up to thread groups, here from 1 to 4. We define the thread group here. This is called, and the thread are numbered from 1 to 16, which is the ND thread. This numeration here is called absolute numeration. However, within a thread group, here from the first thread group, each thread has its own index starting from 1 to the number of threads within the group. This is called relative numbering. The numbering is relative to the thread group. You can also use the all keyword to use all the threads defined in the group. CPU core here are numbered from 0. Thread groups are numbered from 1, and thread ID from 1 as well. Once you define groups and CPU maps, you can attach them to a byline using the thread keyword here. This keyword replaced the one that you had before, which was a process where you can bind assign a CPU, you can assign a thread to a byline. Now you will use the thread keyword. Since only one thread group can be defined on a byline, you have to declare several bylines if you want to use several thread group on a proxy. For example, in this one, proxy one, we use two groups, the group 1 and the group 3 within the same proxy. You can also use a shard directive, shards directive. This allows to create listeners for this byline. It can be useful if you have a large amount of threads to prevent locks in kernel when new connection arise on the servers. You should check the documentation for other details about how to use shards, but it's important to not use shards within a port range because it will create a file descriptor per thread and per port. For example, if you have 100 ports range and 8 thread in a group, the shard directive will force the creation of 800 listeners. So you can do the math with 1,000 ports and 64 thread. You will consume a huge number of file descriptors. When you have a dual socket CPU, I mean two physical CPU in a server, they communicate through a QPI, which is a quick path interconnect. This interconnection has latency between core from socket 0 to socket 1. For example, if core 0 want to communicate with core 4, it has to go through the cache and the QPI to reach its partner. This is an example of the C2C core-to-core latency tool on a dual socket Xeon machine. It shows the impact of the QPI between sockets. We can see this one. We have 2 sockets, 2 physical and 10 physical and 10 logical cores per socket. It means a total of 40 cores, 2 L3 caches, 1 per socket. Access within the same socket are the same as a single socket CPU. I mean 20 nanoseconds from physical to a logical core, 100 nanoseconds within the same socket, but when you communicate from one socket to another one using the QPI, the latency drastically increase up to 250 nanoseconds. So the cost of the QPI is about 150 nanoseconds. Now you can understand why you may have better performances on a single CPU machine than a dual CPU one, especially if you don't bind a HAProxy thread into all the cores of a single socket. If you have the thread spread across all the cores, it will increase the latency and decrease your performances. So it's better to bind HAProxy on one single socket and use the other socket for some other tasks, such as for example, to process requests across a WAF. Okay. Now for the thread groups, they are useful if you want to go beyond the 64 thread limitation. you should create 2 groups of 48 threads on a 96 core CPU. You should also limit the usage of the QPI on dual socket CPU. You should create 1 group per CPU. You can gain performances on AMD machines by grouping thread per CCX, core complexes. So the question, do you really need a thread group? Well, the answer is not very clear. It's not sure. It really depends on how on your setup. If you have AMD machines, yes, it would be useful. If you have a single core, a single socket Intel CPU, well, the answer is not yes, might be no. I did not have access to AMD CPU to measure the latency between the cores. So I couldn't run the C2C LAT on that kind of machine to see the thread, the latency involved by the QPI. Well, if you want to know how to bind, how to use group, you should really use the C2C latency to check what are the best performances for your thread. Okay, now let's go with another key feature for the 2.7, which is the bandwidth limitation. The bandwidth limitation is defined using filters. You can use the filter keyword in the configuration in a front end or listen section. Each bandwidth filter can be applied using routing rules such as TCP request or HTTP request rules. We'll see an example later. There are two types of bandwidth limitation. The first one is per resource limitation. This one. If a 10 megabyte limit is set for a resource and each stream can use up to 10 megabytes per second bandwidth. In this example, we can see that each streams are consuming 10 megabytes. And the other limitation is the share bandwidth or the stickiness limitation. It's called a stickiness limitation because it uses a stick table to limit the bandwidth. For example, with a share bandwidth of 10 megabytes, each stream will consume 2.5 megabytes per second. The bandwidth is divided equally between all the streams. The bandwidth limitation can be set for inbound or upload streams or outbound or download streams. But in a real world, almost nobody uses inbound limitation, but your mileage may vary. We mostly use outbound limitation. Let's see stream limitation. So this setup is for a stream limitation. We create a bandwidth limit called limit by stream with a default limit, which is 10 megabytes, and with a default period of 1 second. This means that the total bandwidth per stream would be 10 megabytes per second. We can use this filter within HTTP request rules using the set bandwidth limit and having the name of the filter that we defined previously. We can also update the limit depending on the resource. For example, in this one, for the /1m, we want to limit the bandwidth to 1 megabyte, and to the 1G, we limit the bandwidth limit to 1 gigabyte, 1 gigabyte per second. Be careful, because the limit here is integers. The documentation is not very clear about that. You cannot use a human readable number, but we are working on that. So make sure that you use integer numbers. Well, we can have a quick demo of that. Okay. Okay. Okay, this is my configuration, which is almost the same as we used. I showed you on the slide. Here we can grab a resource. Oh, I need to start HAProxy. Sure. Okay, here we can see the bandwidth limit is 10 gigabyte, which is the default bandwidth limit. The injector 7 here is the same host, and we can see that they are all downloading at 10 megabytes. If I want to get another resource, such as the 1 gig, here we can see the bandwidth go up to 1 gigabyte. For the 1M, the bandwidth is 1 megabyte per second. So we can really define, have some fine control on the bandwidth. Okay, let's get back to the presentation. Okay. Yeah. Okay. The other one is the other limitation is the shared limitation. It's using stick tables. Here we define a stick table which is called limit by source, SRC. It computes the download rate over a period of 1 second, and it's per IP. The filter limit by source use the SRC IP as a key to limit the bandwidth, and we define 10 megabytes bandwidth limit per IP address. So each client would be limited to 10 megabytes per second for all resources, except for /unlimited. Okay. It's important to notice that in case of shared bandwidth, the limit cannot be adjusted by routing rules like we did before. So this limitation is a hard limit, and you cannot modify afterwards. So let's have a quick look at an example. Okay. Here is my configuration file. Oh, I didn't show you before the version that I use. I use HAProxy 2.7. So I start the proxy, and okay. This client is using, it's transferring at 10 megabytes per second. the other one as well. So the two clients are transferring at 10 megabytes per second. And this one, this window here is the same client as this one. And when I start a transfer, okay, you can see the bandwidth is starting to equalize itself to 5 megabytes per second, which is 10 divided by 2. But if I want to download the unlimited resource, they are not impacted. Okay, so because there are different streams. Okay, there are some limitations, some things that you have to take in account with the bandwidth limitation. Because filters cannot be defined in the default section, bandwidth limitation cannot be defined in the default section. It has to be defined in a proxy definition. In HTTP mode, only the payload is subject to limitation, not the headers. The filter order is important as well. If, for example, you use a compression filter, the bandwidth limitation is limited to the compressed data, not the original payload. The limitation acts at stream level inside HAProxy for forwarded stream only. It means that once the transfer are started, the limitation cannot be changed unless, except for shared bandwidth, where the limitation adapts to the number of streams. Okay, now let's have a look at some other changes added to the 2.7 release. Stick table have been reworked. It used a simple lock mechanism. It was introduced in 1.8, HAProxy 1.8, and almost 95% of the time was spent waiting for lock in some large setup. The locking mechanism has been relaxed and performance gain and raised with a factor about 11 on heavy loaded environment, especially when track SC rules are used. Under the hood, instead of using a spin lock, this is a case where a lock is required for each access to the table. Read-write lock is used now. It only requires a lock when a thread wants to write in a table. So that's why we can gain up to a factor of 11 on a heavy loaded system. The other change about the stick table is now you can define sharding by the use of shards keyword in the peer section. The idea behind this this new feature is to send only a portion of the table to each peer and have a centralized aggregation of this table. For example, in this example, we use 2 shards, and half of the keys are sent to the first peer, and half the keys are sent to the second peer. The table sharding really makes sense in large environments with the combination of the stick table aggregator from the Enterprise Edition So if you don't have a very large environment, maybe this feature is not for you. But if you have a very large environment and you use the stick table aggregator, you can gain some performances because you will reduce the traffic sent to other peers. Small update happened to Lua as well. Now scripts have the ability to accept an argument at load time. It's very convenient to pass environment variables to scripts or some other parameters. A script can retrieve its argument via the table.pack function, as we can. Where's my mouse here? Table.pack here. Yeah, be careful about the three dots. This is because pack is a variadic function. So the three dots syntax allow arbitrary number of arguments. In this example, the log.lua script is loaded with two arguments, hello and 1, 2, 3. The Lua stores the script arguments into the args table, and then you can access their value using regular tables. Be careful because in Lua, an index starts from 1, not from 0, like you would see in most languages. Quick support is still not activated by default. The reason is that it requires quick compatible libraries such as quick TLS, which is not shipped in most Linux distributions. So you have to compile HAProxy yourself to test or to use quick. The quick v2 with a quick compatible version negotiation, which is draft 08, has been added to HAProxy. Now the cubic congestion algorithm is supported. Basically, cubic is a little more aggressive than the on packet loss than the Neueno algorithm. Well, the details for the congestion algorithm goes beyond the scope of this presentation, but you can still check Wikipedia for details. Quick stability has been increased. HAProxy.org uses quick for several months with any impact. So if you want to try it on production, you can still follow the HAProxy.org setup and run two instances of HAProxy. The first one is announcing quick to browser. If the second one, which is serving quick, is alive, you can check HAProxy.org for more details about that. New converters have been added. The table expire. It returns the remaining time before a specific key will expire in a table. The table idle is a similar converter that returns the time since the key has been last updated. The host-only converter trims the ports from the string that contains the host header. Prior 2.7, we should use this line, the request header host, and split the host name using and take the first argument using columns and lower down the value to get the host name. Now you should be able to retrieve the host name only using the host only converter. It trims out the port from the host name header, and it will lower down the case for you. So you only have one converter. Similar to the host-only port, you have the port-only. It retrieves only the port from the host header for the string having the host name, the value from the host header. Another one is the X509 VAR string. It converts numerical value into the constant name as defined in OpenSSL code. For example, instead of having the second line here, if you want to verify SSL certificate before 2.7, you have to check this value against the number 10. Now you can convert this number into a string, and it's more convenient to read the configuration file because nobody knows that the internal code 10 is because the certificate has expired. So now you can see just with one glance in the configuration. Some other changes, you can use the -dc and -dc key to dump a configuration file. This is very convenient if you want to share your configuration on the internet, to forum or GitHub. The DC-key version tries to anonymize the configuration by removing host names and IP addresses. I can show you an example of that here. Okay. Okay. The -dc here, okay, it dumps out the configuration without any comment. And if I want to anonymize my configuration, I can put a random key, and you can see the host names, the IP addresses are obfuscated, so we cannot. You can safely share your configuration on the internet without having to put some random data, imaginary IP addresses. The master socket now can be, which is used to operate on several commands, such as the reload command. When you send a reload command to the master socket CLI, the status of the new forked process is shown to the client. In this example, something went wrong with the reload, so the success value is set to 0, and the alert and notice warning are shown on the command line. The main purpose for this feature is to inform some automated tools such as the Runtime API and some other in-house tool to know the status of the reload operation. Well, thank you for your attention. Do you have any questions? I see one. Oh, regarding the bandwidth limitation, Rock said probably the bandwidth limit is megabits per second and not megabytes. No, in the case of HAProxy, in this this setup, the value is expressed in bytes, I really mean bytes, not bits. So be careful about that, because you may not be sure about what you are configuring. The limitation is really megabytes, not megabits. Do you have any other question? Oh, the CPU affinity on virtual machines. Well, this is a tricky one, because I would say it really makes sense if your hypervisor uses the CPU affinity as well. Otherwise, you don't know really what you are doing. When you are using virtualization, you have several layers of abstractions, so you won't get some great performances. So, well, I will tend to answer no to this question, because the process would be mapped to a virtual core, which is emulated from the hypervisor, and not to a physical one. But I'm not sure this will make sense to use CPU affinity with virtual machines. But you can still use it in the configuration, but I'm not sure that you would gain any performances. Okay, maybe some other question? Don't be shy. Okay, so thank you for your attention again. Okay, thank you, Anders. Have a nice evening as well. So have a great rest of your day, everybody, and see you for the next webinar. Bye.